Hello. All right. So we're back. We're gonna continue working through Dummit and Foot, and today we're about to start chapter 3, which is secretly chapter 4, because this book has a chapter 0. So far we finished 3 chapters, just pretty good progress. It's been what, like 3 weeks of streaming, and we finished 3 chapters in 3 weeks. I would say that's pretty good progress, actually. So yeah, it's time to start chapter 3 today. So today's section is actually pretty long. It's the definitions and examples section within the chapter called quotient groups and homomorphisms. So yeah, this is I would still say we're, kind of in the basics of group theory right now. And yeah, this quotient group stuff, it's useful stuff to know. So I'm just gonna keep track of our definitions by writing them over here. Yeah. So okay, here it says, in this chapter we introduce the notion of a quotient of a group G. It's another way of obtaining a smaller group from the group G. We'll use quotient groups to study the structure of G. For example, we should see that in the lattice of subgroups for a quotient of G is reflective at the top of the lattice for G, whereas the lattice for a subgroup of G occurs naturally at the bottom. Yeah, I'm sure they'll go more into that. Study of quotient groups is essentially equivalent to the study of homomorphisms of G. If phi is a homomorphism from a group G to a group H, recall that the fibers of phi are sets of elements of G projecting to a single element of H. You can represent pictorially. So if there's a bunch of stuff in the group that all gets sent to the same place by a homomorphism, then this altogether is the fiber of this guy. Okay, the group operation provides a way to multiply 2 elements in the image, suggests a natural multiplication of fibers lying above those 2 points, making the set of fibers into a group itself. Yeah, that's pretty weird. Right, the set of fibers is itself always a group, so I guess the set of fibers is the set containing 1, 2, 3, 4, and 5 things of its own. And the set of fibers is going to be in bijection with the image of phi. And the image of phi is a group, which is to say that these 5 points in H, you can multiply them and divide by them, and there's associativity and all of that. And so you can kind of take that group structure and embed it onto the structure of the fibers. So the fibers inherit the group structure from these points. This multiplication is associative. Okay. Here the group action, the group law is as follows. So if X and Y are inside this set, so real. What do you mean, Gov? Yeah, so if X and Y are 2 fibers inside this set. Alright, yeah, go ahead. Let me know. So if X and Y are 2 fibers, such that X is, equivalent to the fiber of, I don't know, A, and let's say Y is the fiber of B, then we define the product of X and Y to be the fiber of the product A and B. Hi Fast64. Do I have a Discord? I don't, but I'm actually working on that. I was probably gonna set that up like today or tomorrow. So soon, but not yet. For the time being, you could probably just post it here. Okay, so you can get a group from any homomorphism by essentially quotienting out by the kernel. Okay, let's take a look at your question, Gov. Ooh, this is hyperbolic trig. I am not at all good at that. I actually have not worked with these at all. Hyperbolic trig, hyperbolic sine inverse is equal to ln x plus x squared plus 1 to the 0.5. Determine the indefinite integral. Oh my god, calculus? You're really gonna make me struggle here, Gov. I haven't even thought about calculus in I don't even know how long. So this is what you want, and you want to use this. So okay, wait. Let me take a stab at this. Even though I'm warning you, I'm probably not gonna make any progress on this. So this is the square root of 1 over x of this, right? Yeah. Yeah, so whenever you want to integrate 1 over something, it just turns into ln of the same thing. So I guess the square root of that. Then we have to divide by the derivative of this inside stuff as well, right? Isn't that how it works? I don't remember, if I'm being honest. I'm sorry, Gov. Maybe there's someone else in chat who can help you. I haven't even thought about calculus in God knows how long. Alright. Yeah, I'm gonna keep working on my group theory. Thanks for humbling me, though. I appreciate that. It's always good to remember how much I suck at calculus. Because that's gonna be chasing me my entire life, I can tell you that. Alright. Definition of a quotient group requires this map explicitly. We show that the fibers of a homomorphism can be expressed in terms of the kernel of the homomorphism. Right, so knowing the kernel is enough to reconstruct what the homomorphism is. I think that's what they're trying to say here. Okay, so let this be a homomorphism with kernel K. Take some fiber. Right, so this is just expressing these as cosets. Right, so they're just saying that, look, fibers are cosets. A physics degree was not the one for you. Do you regret studying physics? Or are you just frustrated with homework? Okay, so this is just saying that fibers are cosets. And this is with left cosets and right cosets. So I guess I should even say our left and right cosets. Yeah. I feel you, Gov. How much of university do you have left? Yeah, okay, I'm not gonna look at the proof of this. Doesn't seem that important. Okay, now they actually define what cosets are. So let me write this down. This is an important definition. Oh, you're in your first year. Good luck. You have... Okay, only 2 years more to go. So I take it you're not studying in the US? That's what I studied, and I feel like almost all colleges in the US are 4-year programs, but I don't know. UK, yeah. Okay, so for any n a subgroup of G, and G living inside it, this is notation for the following set. The set of all multiples you can make by multiplying this particular G with any n inside this. So it's like multiply the element with the set, pointwise. And the same thing but on the right hand side. It's like this. So you have the left and right cosets. And this looks... Alright, so how would we prove something like this? So this is saying that if U is in X and W is in XY, then find something in Y such that U times that something is equal to W. That's essentially what we need to do here, right? So I'm gonna ditch this stupid notation of x and y and say that, okay, look, u is an x, and that means I can write x as uk. That was one of the propositions we saw earlier, that look, this is actually a coset. And then similarly, z is actually wk. So we want some, I guess, v in y such that uv equals w. My music is being so weird. Turns out to be y, something like this. Is this what you're saying? Because yeah, FAST64, I think you're right about that. So, yeah, I think, what you're saying is kind of the same thing anyway. Alright, so first off, because A is abelian, B is in fact a normal subgroup of A. Because if G is in A and B is in B, then G, B, G inverse is the same thing as G, G inverse B, because we're abelian, which is just B, and so is certainly inside B. So B satisfies the normality condition. And that means that A over B is a well-defined group. Alright, great. Now we just need to show that this is abelian, right? So consider the inverse image of G and the inverse image of H. This is defined to be the inverse image of GH, but that turns out to be the same thing as the inverse image of HG because the group is abelian, so GH is the same thing as HG, which we can now break up once again as the inverse image of H times the inverse image of G. So look, these elements are the same, which means that A mod B is abelian. And we're done. Question 4. Prove that the quotient group G mod n, in the quotient group, that coset, okay. This is just using the group rule. Right, so G mod n quotient. We want to show that Gn to the A equals GA n for any A in the integers. But look, this is not so hard. Gn to the A is just Gn times Gn times Gn, like A times. And then you can like fold up each multiplication individually and get G squared n. And you keep going and you just get GA to the n. Like, I don't know what to say here. This is pretty straightforward. I guess like if we were being rigorous, we'd also have to show this for inverses. But that also comes from how we define inverses in the group itself, so it's not too difficult. Use the preceding exercise to prove that the order of the element Gn in G mod n is n, where n is the smallest integer. Okay. I think we've already proved that. Exactly. We've already shown this for homomorphisms, so it just happens to also be true here. Okay, so let this be a coset of G. Then the order of this guy equals n, where n is the smallest integer such that G raised to the n is an element inside n. So the way to think about this is that, look, in G mod n, Gmod n is essentially the group you get by deciding that from now on n is the identity. Everything in n is the identity. And so if g to the n is an n, then certainly gn to the power n turns out to just be g to the n, as we showed in the previous exercise, which is just n because g to the n is itself inside n. Which is the identity. Which is the identity in Gmod n. And since nothing smaller than this puts you in here, right? If m is smaller than n, then gn raised to the m is just gn to the n, right? Which is not equal to n anymore. That should be an m. Because g to the m is not inside n. Yeah? So that should prove that. Question 6. Okay, we're defining a homomorphism from the multiplicative group of real numbers 2 plus minus 1. Okay, so it's just sending any element to its sign, right? So it sends the element x to the absolute value of it, to x divided by the absolute value of it. Yeah. So for example, 5 gets sent to 1, -7 gets sent to -1. So it just picks out the sign, really. Describe the fibers and prove that this is a homomorphism. Alright, I guess. Why is this a homomorphism? Let's say we have x, which goes to x over this, and y goes to x over this. Then look, xy gets sent to xy over the absolute value of xy, which is the same thing as x over the absolute value of x multiplied by y over the absolute value of y. And so it's a homomorphism. So phi is a homomorphism. And then we needed to describe the fibers, right? So what is the inverse image of 1? Well, it's all the positive real numbers. And then the inverse image of -1 is all the negative real numbers, which I'll write like this. And I think that's it for this question. So now question 7. That was a weird question. Yeah, I guess this, picks out the fact that doesn't matter how big your numbers are, positive times positive is already positive, positive times negative is always negative, negative times negative is always negative, and x plus y, which is pi of ab plus pi of xy. So it's a homomorphism. We've got that. What about surjectivity? Why is it surjective? So let this be some real number. Then look, phi of the number r comma 0 goes to r plus 0 is equal to r. So yeah, we've got surjectivity as well. Like, no matter what element we have on the right hand side here, we can find something on the left that gets sent to it. And then we want to describe the kernel and the fibers geometrically. That should be fun. So let's draw a picture. Here's R2. And what is this really doing? It's taking this length and kind of adding them together. So it rotates this. So I guess this point gets sent somewhere here. Like that. I don't really have a really nice geometric way of doing this. I guess, yeah, the nice geometric way really just comes down to take a point and then just rotate it down along this way. And this is where it gets sent. So the map is kind of is things that look like this, where B and C are in F and C is not 0. That's the kernel. Okay. And then fibers are kind of similar. Fibers, you know, instead of 1 here, you just stick in whatever the thing is whose fiber you're looking for. Okay, part B. Prove that the map psi, another one. This time it goes to the vector AC from G to F star cross itself. Describe the fuck this shit. Okay. I guess this is what we're stuck with. What are you playing? Cool. Okay, so the homomorphism. Why is this a homomorphism? Okay, I'm just gonna, you know, appeal to this thing here. That phi of the product AB0C times DE0F is just AD, comma CF. And then be like, look, this is also just A comma C times D comma F, which is exactly phi of this and phi of this. So it's a homomorphism. Okay, what about surjectivity? Yeah, given any pair A comma C and F star cross F star, we have that this A times this C is not 0 because A itself is not 0 and C itself is not 0. And so phi of A10C gets sent to A comma C, and we have surjectivity as well. What about the fibers and kernels? Well, the fiber is the stuff that gets sent, sorry, the kernel is the stuff that gets sent to 1 comma 1, so it's all matrices of the form 1 1 0 and B here. AC is not equal to 0 by definition of G as well. Equal this stuff, that's the kernel. Prove that H is isomorphic to the additive group F. So H is the kernel from before. Now let's see what happens when you multiply something that looks like this with something that looks like this. What we get is we get a 1 here. We get an E plus B here. A 0 and we get a 1 here. So multiplying actually just has the effect of adding. So you can make a map from H to F plus, right? That sends the matrix 1B01 to the element B. And this is an isomorphism for this very reason, that look, when you multiply them, you get the sum here. So it's a homomorphism. I guess we also need to show injectivity and surjectivity to get that it's an isomorphism. But the other thing we could do is just define an inverse from F as an additive group to H that sends the element B to the matrix 1 0 B 1. And then this same equation shows that this is also a homomorphism. And then look, these guys are clearly inverses, and so we're done. It's an isomorphism. All right, question 12, algebraic topology time. Yeah, so this question borrows some concepts from algebraic topology, which is pretty cool. So G is the additive group of real numbers. H is the multiplicative group of complex numbers of absolute value 1. So it's just the unit circle living inside the complex plane. Let phi be a map from G to H that sends R to this number. So I guess, yeah, to make sense of this question, you kind of got to know what, like, e to the I theta means is a complex number. And if you haven't seen this before, then this as a complex number is just the number with angle theta and radius r. So this corresponds to this point here. And so when we have the map that sends, I guess that goes from the real numbers to h, or the unit circle, that sends r to e to the 2 pi I r, then essentially it's sending the real number r. How do I explain this? Yeah, I guess this picture is like the nice way of doing it. Let's suppose that this here is 0, this here is 1, this here is 2, this here is 3. So we've kind of wound the real line up in this spiral fashion. So for example, 0.5 would be somewhere back here, and then 1.5 would be somewhere back here, similar, so on and so forth. All this is doing is it's saying, let's say we have the point 0.25, then you're going to go 0.25 around the circle. And so this point gets sent here. And this notation is useful because, look, here is 0 in the circle group. Or I guess one would really call this 1 in the circle, in the complex plane. That's 1. And then this is I. So the kernel is everything that gets sent to 1. So it's just this line up here. It's all the integers, essentially. So draw the points on the real line which lie in the kernel. I've drawn those. Describe similarly the elements in the fiber. So let's say we wanted the fiber of I, which is over here. Then we would just look at all these rightmost points over here. So this is like, I don't know, it's such a nice geometric picture. I really like it. The fibers of -1 I, so -1 is over here, and so the fibers are kind of the points back here. And then e to the 4 pi I over 3. So this is what? This is 2/3 of the way around the circle. So 2/3 of the way around the circle is like here. So the fiber of this guy is all of these points back here. Up this way and down this way. So hopefully this geometric picture makes sense. So I think that's about it for this question. We can just move on to question 13. There is a lot more going on here than just, the group. Like, we can think of these, of the real line and the circle as what are called topological spaces, in which case this is not just a group homomorphism, but even, I guess, a continuous covering map. Those words probably don't make much sense if you haven't done algebraic topology, but there's more stuff happening here than just algebra, is the point. Okay, repeat the preceding exercise with the map phi replaced by the map that goes like at twice the speed, essentially. So this time, phi is a map from R to H, being the circle group, that sends the point R to e to the 4 pi I R. So if we draw this picture again, where this is our circle, once again, our real numbers are spiraling above. I'm so bad at drawing that spiral. Okay, there we go. That's okay-ish. It's also a Lie group homomorphism. Good to know. Yeah, there's so many ways of thinking about this. So this time, if this is 0, let me just draw the points again. Here's 1, here's -1, here's I, here's -I. Okay, so this time, it's not 1 that we draw here, it's 1/2. And then 1 is up here. And then this is 1.5, so 3/2. So we've like wound out this circle like at twice the speed, in a sense. Last time we had 1 showing up here, but this time this is only half of that distance that we've curled up into a circle. And yeah, in the same way, the fiber of 1, i.e. the kernel, is all of these points. So 0, 1/2, 1. It's all the integer multiples of 1/2, right? So the kernel of phi is equal to the integer multiples of 1/2. So this. Yeah. And the fibers you can figure out similarly. Like the fiber of I is going to be 1/4 of the way from 0 to 1/2, then 1/4 of the way from 1/2 to 1, so on and so forth. Hello. How are you?
Good. What's up? Did you make progress?
Doing some math.
Oh, are you on chapter 3 now?
Yeah, we're on chapter 3. Yeah.
Hello, Infast64. I see you on here all the time. That's great.
Yeah, Fast64 is kind of an OG fan.
Yeah, I saw the overleaf document.
Really Fast64, about the overleaf document. I wanted to ask if I have permission. I think you mentioned this before, but I just wanted to make sure. I want to check if you are okay with me sharing the link to the overleaf somewhere on this channel so that others can take a look at it. And I'm thinking of in my channel banner putting a little blurb of this question that we're working on so that anyone who visits the channel can think of it too and see the notes there. And then Aryan was also going to help me make a Discord, either today or tomorrow. Because someone actually asked about a Discord today earlier. Yeah. And I was like, okay, we need to get on this.
Yeah, we'll set it up today only.
Yeah, so we'll set up the Discord later today, and then we can even put it in there and have channels for fun problems that we can all work on together. I think that'd be fun.
Okay, cool. We'll do that. Have fun.
Fine, let's say. It's totally disconnected. Is that a thing? That's interesting, Fast64. That all profinite topological groups are totally disconnected. I wonder if that's the case. Okay, so we have A over B times B is equal to A, which is in the integers. And as we showed in whatever question, right? So this means that the order of A over B divides B. There was some question somewhere where we showed, what's this? Yeah, question 5, right? Where the order of a coset like this is the smallest positive integer such that that element. Prove that Q mod Z is isomorphic to the multiplicative group of unity. All right, let's construct a homomorphism. So here's Q mod Z. And then here's the multiplicative group of unity, which I think we had called Z earlier. So I'm just going to call it capital Z. Roots of unity. And we're going to send RZ, where R is, the unique representative between 0 and 1. So RZ gets sent where? Gets sent to E to the 2 pi I R. Yeah. Then this way, okay, so first we need to show that this is a homomorphism, right? So how do we do that? Let R and Q both be inside the range from 0 to 1 and rational numbers. Then RQZ gets sent to E to the 2 pi I RQ, which equals E to the 2 pi I R times E to the 2 pi I Q. Wait. This is an additive group. This is R plus Q. There we go. I was confused there for a second, but I think I figured this out. There we go. Yeah, so this element gets sent here, and so it is a homomorphism. Okay, next we want to show surjectivity. Let Z be inside capital Z. then because it's a root of unity, there exists, I guess, let's find out what the order of n is. So let n be the order of z, which is to say that z to the n equals 1. This means that z... This means that z is equal to e to the 2 pi I a over n for some a in 0 to n minus 1. So look, we have that phi, or whatever this homomorphism is, I'll call it phi. Phi sends a over n to z. So we're done. We have surjectivity. Okay, and now we need to show injectivity. Let R and Q both be in this 0 to 1 range. And let's suppose that e to the 2 pi I r equals e to the 2 pi I q. Well, this means that 2 pi I r and 2 pi I q are some multiple of 2 pi I apart. That's the only way these two angles make the same point, if they're a full circle apart. Which means that, factoring out to 2 pi I, r is equal to q plus n. But look, r and q are both in this range, and so n has to be 0, which means r equals q. And we have injectivity as well. So we've made our isomorphism, and I think we should be done. Okay, we can keep going. There's so many questions in this section. I think I'm gonna... And look how many parts each one has. What is this? This is gonna take so long. It's fine. It's fine. We're doing it. We'll see how much we can get through today. How long have I been streaming today? It's been almost 2 hours. I can keep going for a little bit. Prove that a quotient of a divisible abelian group by any proper subgroup is also divisible. So let A abelian and divisible, right? So divisible just means that for every element A inside the group A and every n inside the integers, inside the positive integers, there exists a B also in the group such that B to the n equals A. So every element has an nth root. That's what it means to be divisible. Okay, now we want to show that if B is a subgroup of A, then A mod B is also divisible. So let's suppose that AB is a coset in here. We want to find something whose nth power is this coset, right? Now, let n be some positive integer. Then there exists B in A such that B to the n equals A, which means AB is actually B to the nB, which is the same thing as BB to the nth power. And so A mod B is in fact divisible. And that's why Q mod Z is divisible, because in a previous section we had shown that Q is divisible. Again, I remember doing this when I was learning about homological algebra, I remember having to show that Q mod Z is divisible. I just don't remember how divisibility relates to homological algebra anymore. This was only a few months ago. My memory is not good. Okay, G is a group, N is a normal subgroup, there's the quotient group. Prove that if G is generated by X and Y, then the quotient group is generated by the images of X and Y. Prove more generally. Yeah, I think I'll just prove the more general statement and not have to prove this one. Right, so let's say that N is a normal subgroup of G. And let pi be the natural projection from G to G mod N. Right, now suppose that G is generated by a set S, where S is some subset of G. Then look at, I guess we want to show that G mod N can be generated by the image of S under this quotient map, right? So let G be an element of G, right? I guess let me do this a proper way. So let Gn be an element of G mod N. Now G is generated by this, so G can be written as some product of S1, S2 times Sn, where each Si is some element in S. Because G is generated by the set, every element in it can be represented as a product of elements from that set. This means that Gn secretly is S1n times S2n times Snn, which means that